It's actually pretty wild when you think about it. How exactly does a machine create a real, tangible, physical object directly from a computer design? And maybe more importantly, why are polymers the absolute go-to materials for this whole additive manufacturing process? Well, welcome to this explainer. Today, we're going to completely bridge the gap between microscopic chemistry and macroscopic 3D printing performance. Think of this as your digital smartboard masterclass. So, here is the million-dollar engineering mystery we need to solve today. It really all comes down to how molecular structure dictates physical reality. The exact way those microscopic, invisible chains are arranged, that directly decides if the gear you just printed is going to shatter under pressure or if it'll run smoothly for years.
All right, here's our roadmap for today. We'll quickly run through polymer foundations, structure and crystallinity, mechanical properties, 3D printing polymers, material comparison, and finally, some real-world exam-focused questions. Let's get into it. Okay, Section 1, Polymer Foundations. Before we can print anything layer by layer, we really need to understand the absolute baseline. What exactly are the materials we're feeding into that extruder?
The crucial thing to remember here is that polymers are just massive macromolecules made of repeating tiny units. Those are your monomers. Picture it like a bunch of individual, colorful links snapping together to form a huge chain. That's polymerization. Now here's the catch. Not all the chains in a piece of plastic are the exact same length. To measure how uniform they are, we use the polydispersity index, or PDI. It's just the ratio of weight average to number average molecular weight. If you have a PDI of exactly 1, that means every single chain is perfectly uniform.
Now, why do we actually care about these two different averages? Well, MN, the number average, is super sensitive to small, lightweight molecules. But MW, the weight average, that one gives way more importance to the heavier, longer chains. And in 3D printing, that is absolutely critical. Those heavier chains are what drive high viscosity. They make the melted plastic a lot thicker and harder to extrude, but the payoff is a significantly stronger final printed part.
Moving right along to Section 2, Structure and Crystallinity. Let's see how these long molecular chains actually arrange themselves in space, because this is where the physics of these materials really kicks in.
Try to visualize this in your mind. First, you've got long, straight chains. They get deeply entangled with each other, which massively increases tensile strength. Second, what if you add branches, like little side chains? Well, those disrupt how tightly the molecules can pack together, so you end up with a less dense but much more flexible material. And finally, cross-linking. This is when covalent bonds literally lock the chains together into a permanent 3D web. These cross-linked polymers, we call them thermosets, are incredibly strong and handle heat like a champ. But once they're formed, there's no remelting them.
And this brings us to the eternal engineering trade-off: order versus randomness. Most polymers are semicrystalline. The crystalline regions are packed super tight and highly ordered. That gives us massive strength, heat resistance, and chemical resistance. But then you have the amorphous regions. These are totally random, basically like a bowl of cooked spaghetti. That amorphous randomness creates free volume, which gives the material its flexibility and impact resistance. You'll definitely want to jot this formula down. The exact percentage of crystallinity is what perfectly predicts a polymer's mechanical and chemical resistance. You can calculate exactly how ordered your material is with this. It's the sample density minus the amorphous density divided by the crystalline density minus the amorphous density, all times 100.
All right, Section 3, Mechanical Properties. Now we take that microscopic structure we just talked about and translate it into measurable, macro-level strength.
Essentially, how much pulling force can your printed part actually take before it snaps? This equation, sigma equals F over A, defines exactly that, and it is highly dependent on those molecular chain entanglements. If you've got high molecular weight and high crystallinity, your cross-sectional area can withstand a massive amount of applied force before it fails.
But wait, what if you want the part to bend without breaking? Elasticity happens because those randomly coiled amorphous chains uncoil when you pull them and then snap back when you let go. Hooke's law lets us calculate exactly how stiff that material is going to be. Young's modulus, that's the E, is just stress divided by strain. High modulus means it's super stiff. Low modulus means it's flexible and rubbery. On to Section 4, 3D printing polymers. Let's apply all these physics directly to additive manufacturing and look at the 3 undisputed heavyweights of FDM printing.
First up is the absolute powerhouse, nylon 6,6. It's synthesized through a condensation reaction between hexamethylene diamine and adipic acid. But the real secret to its incredible performance, its amide linkages form intense hydrogen bonds right between the polymer chains. That creates insanely high crystallinity, giving you phenomenal tensile strength and wear resistance. Literally the ultimate choice for load-bearing stuff like gears.
Next, we've got PLA, or polylactic acid. This is everyone's eco-friendly favorite for prototyping, mostly because it's derived from renewables like cornstarch. Thanks to its flexible chains, it has a really low glass transition temperature. That means smooth melting, almost zero warping, and it's just ridiculously easy to print. Plus, those ester bonds make it completely biodegradable over time.
And then there's ABS. ABS is a really clever copolymer with a two-phase structure. The butadiene gives it a rubbery phase, so it can absorb impacts, while the styrene and acrylonitrile provide a rigid phase for strength and heat resistance. It's amazing for durable parts, but fair warning, thermal contraction makes this stuff notoriously prone to warping as it cools down on the bed.
Okay, Section 5, Material Comparison. Let's put these three head-to-head so you know exactly what to choose for your next project.
Take a good look at the trade-offs here. PLA is a breeze to print with, basically no warping, but its heat resistance is terrible. ABS sits right in the middle. Great strength, but you absolutely need a heated bed to fight that warping. And Nylon 666? Yeah, it's genuinely difficult to print, but if you can pull it off, it rewards you with massive strength and amazing thermal stability.
Finally, Section 6, Exam Focus. Let's put everything we've talked about to the test with some real-world application questions. Okay, imagine this scenario. You need a printed part for a car engine compartment. It's going to face high heat, serious mechanical stress, and fuel exposure. Thinking back to our chat about intermolecular forces and free volume, which of our three materials actually survives the engine bay? If you said Nylon 666, you hit the nail on the head. When you're explaining this, your magic keywords are hydrogen bonding and high crystallinity. Those strong hydrogen bonds provide the thermal stability to survive engine heat. And because that crystalline structure is packed so tightly, there's practically zero free volume for fuels or solvents to penetrate. PLA would literally melt in there, and ABS would just degrade from the fuel.
All right, last test. Let's connect the actual cooling process of the printer directly to the macro strength of the part. Say you have two identical nylon samples, but one is cooled slowly and the other is cooled super fast, changing their crystallinity. Which one do you want for a load-bearing part?
For sure, you want the sample with higher crystallinity. By letting it cool in a way that maximizes order, you get those tightly packed chains and reduced free volume. That extra intermolecular attraction gives you way higher tensile strength. Just a quick pro tip for printing though. While maximizing crystallinity gives you great rigidity, if you cool it too fast trying to force it, your layer adhesion is going to suffer.
Keep this revision summary handy. It's basically your ultimate cheat code. It perfectly links the invisible microscopic properties to the physical macroscopic effects, and exactly what that means when your extruder gets to work. High molecular weight means strength but tricky extrusion. Crystallinity brings the heat resistance. Ester linkages equal biodegradability, and two-phase structures give you that impact resistance. So next time you're holding a 3D printed object, ask yourself, what invisible molecular architecture is holding that reality together? Thanks for hanging out for this explainer, and keep exploring.